Welcome to Unit 4, Lesson 2, Function Notation. We have 3 learning goals for this lesson. Number 1, I can use function notation to express functions that have specific inputs and outputs. And what we mean is instead of saying y equals something, we're now going to say a function of some input equals something. So that's what function notation is. We're getting rid of the y and we're changing it to say a function letter of some input. Number 2, I understand what function notation is and why it exists. So we'll show what function notation is, and we'll talk about why this might be more beneficial than simply saying y equals. And number 3, when given a statement written in function notation, I can explain what it means in terms of a situation. So what we want is for you to be able to take a function notation and be able to say, this is what the input is and what it represents in this context, and this is what the output is and what it represents in this context. The height of water in a bathtub, W, is a function of time, T. Let P represent this function. Height is measured in inches and time in minutes. Match each statement in function notation with a description. So, in function notation, first we have the letter. And this letter P represents the function. It's just the name of this function. Whatever is inside the parentheses is our input. And if you remember, anytime you see the words is a function of, what comes after that, time, T, is your input. Whatever comes before the height of water in a bathtub, W, is your output. So inside the parentheses is your input, and what it equals is your output. So when we have function notation, we have function name, the input inside parentheses, and it equals the output. So as we're trying to match these, that's what we're going to look at. So I have an input of 0. So my input is time. So that's 0 time. And an output of 0, which is the height of water being 0. So this means that A matches with number 2. The bathtub starts out with no water. Now we can go to B. 4 is our input, and our input is time. So that is a time of 4 and a height of 10. Now if I look at number 3, it says after 10 minutes, the height of the water is 4 inches. Well, this says the height is 4 inches. We're saying the time is 4, so it wouldn't be 3. Number 4 is the opposite. This says the height of the water is 10 inches after 4 minutes. So if we're saying time is 4 and height is 10, that matches number 4. C, our input is inside the parentheses, and our input is time. And our output is height. So now I want a height of 4 with a time of 10, and that matches number 3. 10 minutes and 4 inches. And finally, our input is 20. That means a time of 20 and a height of 0, which matches number 1. After 20 minutes, the bathtub is empty. So D matches number 1. Function C takes time for its input and gives a student's Monday class for its output. So if you remember, we have name, input, output. Number 1, use function notation to represent a student has English at 10 o'clock. So the function name is capital C. The input here is time, and the time is 10 o'clock. And the output here is the class, which is English. So this would be function notation. Function C, 10 o'clock input, gives us English class as the output. Number 2 wants us to write a statement to describe the meaning of C of 11:15 equals chemistry. Well, this means a student has chemistry class instead of English at 11:15 instead of 10 o'clock. So this is how we can take a description, use a word problem, and turn it into function notation, or take function notation and turn it into a statement. Function F gives the distance of a dog from a post in feet as a function of time in seconds since its owner left. So remember, as a function of, this tells me my input, and this tells me my output. And you can see they have time as the input or x value, and distance as the output or y value. And they want us to find the value of f of 20. Remember that what is in parentheses is the input. So if I want to know what f of 20 equals, I go over to 20 for my input. I go up until I hit the line, and I see that it's right here where y is just above 3 feet. So we could say f of 20 is approximately 3.1 feet. Next, they want us to find f of 140. Again, the parentheses gives us our input. So we go over to 140, and then we go up until we hit the line. And we see that we hit the line about halfway between 3 and 4. So we could say that f of 140 is approximately 3.5 feet. Function C gives the cost in dollars of buying n apples. What does each expression or equation represent in this situation? Anytime they give us the problem in this format, function C gives, it's always going to give the output. And it uses the input to give us that. So now we know that the cost in dollars is our output, and we're using a number of apples as our input. So now if we look here, remember we have the name of the function, the input in parentheses, and it equals the output. So for number 1, 5 is our input, and our input is the number of apples. So this says 5 apples, and it equals the output, which for us in this problem is the cost in dollars. So this says 5 apples costs $4.50. Now if we look at number 2, we don't have an output, but we do have an input, which is 2 apples. But it tells us that it gives us the cost in dollars. So even though they don't tell us what it equals, just the function notation says that this function would give us the cost of 2 apples. We don't know what that cost is, but we do know that's what the function notation would give us. A number of identical cups are stacked up. The number of cups in a stack and the height of the stack in centimeters are related. Can we say that the height of the stack is a function of the number of cups in the stack? Explain your reasoning. We need to go back to the definition of what makes a relationship a function. In order for something to be a function, that means each input has only one output. So, if we say the height of the stack is a function of, That means height is our output, and the number of cups is our input. So every time we change the number of cups, we're going to have one new height. Okay? I couldn't have 5 cups and have it be 6 centimeters and 10 centimeters. So for number 1, yes, it is a function because each number of cups has only one height. Now for number 2, when we see is a function of, remember that our output comes before and our input comes after. So now the height is the input and the number of cups is the output. Again, if I have a stack of cups that is 10 centimeters tall, there can only be one number of cups that makes that stack. I couldn't have a 10 centimeter stack of cups that was both 5 cups and 10 cups. So for number 2, yes, this is also a function because each height has only one number of cups. So in this example, both are functions because both have inputs with only one output for each input. In a function, the number of cups in a stack is a function of the height of the stack in centimeters. Remember, we look for is a function of. What comes before is your output, and what comes after is your input. Number 1, sketch a possible graph of the function on the coordinate plane. Be sure to label the axes. So, our x and our y axes, the x-axis is your input or your independent variable. So in this case, this is height measured in centimeters. The y-axis is your output or your dependent variable. In this case, that's number of cups. And now we can number it. So, if we said the initial cup was 5 centimeters, we could put a point right here. Then if we said every additional cup added 1 more centimeter to it, we could then place more points where every time we increased by a cup, we also increased by 1 centimeter. And this is what our graph would look like. We would only have points because we don't have half cups. If I wanted to pick 1 point here on number 2, identify 1 point on the graph, and explain the meaning of the point in the situation, we could take this point right here at 7, 3. 7 is our input, so that means 7 centimeters, and 3 is our output, which is the number of cups. So a 7 centimeter stack has 3 cups in it.